Okay, in this video series, we are going to discuss singular value decomposition. And this video consists of three parts. In this particular part one, we will be building the basic foundation to derive singular value decomposition. And the basic foundation will consist of understanding the eigenvalues and eigenvectors in combination called Eigen Spaces. And then we will also discuss what are the properties of a particular kind of matrix that is used mostly in singular value decomposition and in other contexts in data science as well. And that matrix is called positive semi-definite matrix. So in this particular part, we will be building our intuition about eigenspaces and positive semi-definite matrices and their relationship together. And in the next part of this video, part 2, we will be actually driving singular value decomposition. Okay, if you ask some expert in data science and machine learning and data analysis that what kind of mathematical concept is mostly used in data science, then maybe most of the people, they land in saying, okay, these are eigenvalues and eigenvectors of matrix. Maybe because whole in optimization theory, most of the convex optimization problems, they land into eigen decomposition of certain matrices. So I thought it is important to spend some time on what do we mean by eigenvalues, eigenvectors, and eigenspaces, because not just in dimensionality reduction, even in several other fields in data science, this eigen decomposition is much more important and much more a core concept that appears mostly in several ways in the solution, in finding out the solution. So let me discuss what do we mean by eigenspace by first discussing what do we mean by eigenvalue and eigenvectors. So consider a square matrix, let's say n by n. Now you might be very expert in saying, okay, a square matrix n by n, which means the column space is in Rn, the row space is in Rn. You might be that fast right now. If you're not, then spend more time and get that quick. Okay. A is n by n matrix. The goal is to find out a vector x, such that if I multiply A with x, the resultant vector, which is in this case, let's say the resultant vector is y, the property of resultant vector y is it is parallel to x. So such a vector x is called eigenvector. This y, the magnitude of y may not be the same as x, or may be the same as x, either way. They may have a scale difference, but their direction is same. So may have a scale difference. May have a scale difference. Or may not have a scale difference. They may be same, y norm and x norm, they may be same or may be different, but what is important is both have same direction, they are parallel. These two lines, they represent parallel. So one way to write parallel is if x and y, they are parallel, one way to write that is y is some value and then x, y is some lambda x. In that way, if we rewrite this equation, then we will say, okay, ax, which is y, is parallel to x, which means is lambda x. So any vector x that preserve its direction, even if a is multiplied with that particular vector x is called eigenvector of this matrix A. So not all the vectors, they preserve their directions. For example, if you multiply matrix 1 to, let me take a simple example, 1, 2, 4, 1, let's say this is a matrix, and you multiply this matrix with, let's say you multiply this matrix with 1, 0, okay, vector 1, 0. The result is vector 1, 4, yeah. The result is vector 1, 4. So yeah, we can expand it column wise. So 1 into 1, 4 and 0 into that. So 1, 4. And now you can see the direction of 1, 0 and 1, 4, that is different, which means this 1, 0 is not an eigenvector of this matrix. So what happens normally is when you multiply a matrix with a vector, the vector loses its direction, it changes its direction. Mostly this happens. But there are some special vectors that preserve their direction. They do not allow their direction to get changed. So the result is, so let me give you an example. For example, 2009, let's say, and I multiply this with, let's say again, I multiply this with 10, and the result is 20, and you can see the direction of 10 and the direction of 20, they are same, although they have a scale difference, but the direction is same. And if in this case, this vector 10 is called an eigenvector of this matrix. And the scale by which this vector basically changes, which in this case can be written as 2 times 10, that scale value is sometimes called the eigenvalue or the corresponding eigenvalue. So the concept of eigenvectors and eigenvalues in a nutshell is that simple. Eigenvectors are those vectors that preserve their direction after multiplication by A. A is some matrix. And remember, A has its own eigenvectors. A different matrix B has its own eigenvectors. So maybe B has its own set of eigenvectors, A has its own set of eigenvectors. The eigenvectors of A are those vectors that preserve their direction after, even if they are multiplied by A. An eigenvector of A may not be an eigenvector of B. B has its own set of eigenvectors and eigenvalues. So eigenvectors and eigenvalues, they are properties of matrix. They are not general. There are no global eigenvectors and global eigenvalues, for example. They are properties of matrices. So why am I talking about eigenspace? What normally happens is if x is eigenvector of A, which means x is lambda x, then any scalar multiple of x, for example 2x, that is also eigenvector of A. So eigenvector is not just, if you have one eigenvector, you have a whole space of that. Every scalar multiple of eigenvector is also an eigenvector. So that's why corresponding to one eigenvalue, you don't have just one eigenvector, rather you have a whole space of vectors, and that space is called eigenspace. Further, for one eigenvalue, let's say lambda 1, you can have eigenspace which is multidimensional, which have more dimensions. So maybe two independent eigenvectors, they both correspond to the same eigenvalue, and the linear combination of those independent vectors make a two-dimensional space, which is a two-dimensional eigenspace. And you can have multiple eigenvalues, multiple eigenvectors for a vector, for a matrix. The matrix must be square. There are a lot of other properties as well. All the eigenvectors might be, all the eigenvalues may be distinct, may not be distinct, they may be repeating. If any eigenvalue is 0, then the matrix is not invertible, its determinant becomes 0. Eigenvalues may be complex, eigenvectors may be complex, although for certain eigenvalues may be negative eigenvalues. So 0 eigenvalue is possible, complex eigenvalue is possible, negative eigenvalue is possible. So there are a whole lot of properties belonging to these eigenvalues and eigenvectors. The most important property that we are interested in is eigenvalues and eigenvectors of a positive semi-definite matrix, because these kind of matrices, they appear mostly in optimization in a lot of models. Okay, now we turn our attention to a positive semi-definite matrix, the properties of this matrix. Let me explain the properties of that matrix, but first let me explain what is a symmetric matrix. If any matrix A, square matrix A, if transpose of that matrix is equal to the matrix itself, then the matrix is called symmetric. So if you have a square matrix, and this property is only true for square matrices, obviously. If you have any matrix and transpose of that matrix is does not change the matrix, if applying transpose of a matrix, by transpose I mean just pick the columns and place them as rows and do this for every column. That is the transpose operation. If doing that does not change the matrix, if the original matrix and the transposed matrix, if they both are same, then we say that the matrix really has a symmetry property, and that matrix is called symmetric. There are several properties of symmetric matrices. Their eigenvalues are all real. Eigenvalues are real, which means there is no complex eigenvalue. The eigenvalues are all real, but the negative eigenvalues may be there, positive eigenvalues may be there, zero eigenvalue may be there, but complex eigenvalue is not possible for a symmetric matrix. Another property is eigenvectors may be chosen orthonormal. What basically happens is for different eigenvalues, for example, eigenvalue 1, eigenvalue 2, eigenvalue 3, let's say there are 3 different eigenvalues. Eigenvalue 1 has an eigenspace, let's say E1. Eigenvalue 2 has an eigenspace, let's say E2. Eigenvalue 3 has an eigenspace, E3. All these 3 eigenvalues all these 3 spaces may have different dimensions. They all are subspaces of the same parent space. But what happens is these spaces are pairwise orthogonal. E1 is orthogonal to E2, the 2 spaces. 2 spaces are orthogonal if every pair of vectors chosen from the spaces, their dot product is 0. So for example, if you pick any vector from E1, any vector from E2, their dot product is 0. And that is true for every pair you pick. Then we say the 2 spaces are orthogonal. So even in E2, they are orthogonal. E1 and E3, they are orthogonal. E2 and E3, they are orthogonal. And that is true even if you have more spaces, every pair of spaces, they are orthogonal. And that gives us that if we pick the basis from E1, and we pick basis from E2, and we pick basis from E3, the basis of eigenspaces, all these bases, they will be orthogonal to each other. And the basis individually, for example, E1 is 2-dimensional. We can pick 2 vectors, let's say B1 and B2. If they're not orthogonal, we can make them orthogonal using Gram-Schmidt orthogonalization. So we can make B1 and B2 orthogonal. But once B1 and B2 become orthogonal, once these bases by themselves become orthogonal, these bases for E3, they by themselves become orthogonal. The spaces are orthogonal, so the overall basis, so all the bases of this and all the bases of that, they are orthogonal. So all the eigenvectors belonging to all different spaces, if you pick them, they can be made orthogonal. And that's property of symmetric matrix. And that property helps in orthogonal diagonalization of symmetric matrix, which is really fast and sometimes become the basic building block for singular value decomposition that we will see in the next video. So next, what we talk about is positive semi-definite matrix. A positive semi-definite matrix, let me call it as S, is symmetric, which means S is S transpose. Any matrix that is symmetric, and all eigenvalues are non-negative. So if you have a symmetric matrix with all eigenvalues non-negative, because it is symmetric, all the eigenvalues must be real. But if negative eigenvalues does not appear, then we say that this particular matrix is positive semi-definite. There are a lot of properties that positive semi-definite matrix inherit from symmetric matrices. For example, orthogonal diagonalization. The other properties are these. S can be written as some matrix times its transpose. So any matrix S can be decomposed. If the matrix is positive semi-definite, the matrix can be decomposed into a matrix times a matrix transpose. Although this decomposition is not unique, but a matrix can always be decomposed in this way. Further, if you have any matrix A and you multiply that matrix with its transpose, the resultant matrix must be positive semi-definite. And this is true even if you have A transpose A. So this particular matrix is always positive semi-definite, and it has a very beautiful role, both of these matrices, this matrix and that matrix. They have a great role in principal component analysis as well as in kernel principal component analysis that we will see shortly, that we will see in detail in the next module. Anyways, if any matrix can be written, if any matrix can be decomposed in this particular form, that matrix is positive semi-definite. If you multiply any matrix with its transpose, the resultant matrix is positive semi-definite. I'm stating all these things without proof. Yeah. So, and further, all the eigenvalues of this positive semi-definite matrix, they are non-negative. So think about an eigenvector of S. So S, let's say E1 is an eigenvector of S. Then SE can be written as lambda 1E, where lambda 1 E1, where lambda 1 is the eigenvalue of S corresponding to eigenvector E1. Think about another eigenvector, E2, which is against, let's say, lambda 2, E2. And let's say this S is n by n. So we have, let's say, n eigenvectors corresponding to their eigenvalues. These eigenvalues, all these eigenvalues need not to be distinct, but they need to be non-negative. If we combine all these, we can write S as E1, E2, En. This is a matrix of all eigenvectors, and all these eigenvectors are orthonormal, because of this process. And this can be written as E1, E2, En times a diagonal matrix lambda 1, lambda 2, lambda n. That's a diagonal matrix. Zeros there and zeros there. If I denote this matrix, which is an n by n matrix, as E, and this is also E, and this diagonal matrix as where the diagonal entries are the eigenvalues as D, you can see SE is equal to ED. That is true for symmetric matrices as well, but all these D values, all the diagonal values in D, they are non-negative. And one more thing, this E, which has all these columns orthonormal, such a matrix is called orthogonal matrix, and inverse of such matrix is just its transpose. So if we multiply E transpose on the left hand side and E transpose on the right hand side, this E transpose, because all the columns are orthonormal, this E transpose acts as inverse of E, and this just cancels out this, and you get this E, D, E transpose, which is sometimes called the, you can call it eigen decomposition of S, or you can call it orthogonal diagonalization of S. There are so many names of this. And we will be using this particular property in the most fundamental concept of the linear algebra called singular value decomposition that we are going to encounter in our next video. So hope to see you in the next video.